Alright, today we're going to start definite integrals and Riemann sums. So the first thing we'll look at is the theorem for 5. It says if f is continuous and non-negative on the closed interval a to b, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is given by this. Let's see if I can draw a picture of this a little bit better so you guys understand what we're doing. So here's my function. It says that it's going to be bounded by the x-axis right here, and then the vertical lines A to B. It's saying that I can find the area underneath this curve by using what's called a definite integral and saying I'm going to find the area from A to B of this function, and what it's doing is just finding the area underneath this curve. So the next part of the definite integrals are these two special definitions. One of them says that if you have an integral from a to a of f of x dx, then you know that the area underneath the curve is 0. So let's see if I can draw a picture of that. If I'm not moving anywhere and I'm finding the area underneath the curve from a to a, I'm not creating any area underneath the curve. And so there would be no area, it would be of A. There would be no rectangles under here is what we can talk about. The width of it would be 0. 0 times the height is still 0. So the area underneath that curve is 0. The last part then I want to mention is that if you have something that's integratable on A to B, then, and we define the integral from B to A of f of x dx, we can flip-flop those bounds, is what we call them, and put a negative out front. Okay, so these are the two special things that we need to remember about definite integral. So what I want to do is we're going to start talking about how we're going to set up a definite integral. We're not going to evaluate this integral. All we're going to do is set it up. So what I'm going to do is I'm going to make an integral sign, and then what I'm going to do is figure out, all right, I'm going to go from what x value to what x value to find the area underneath this curve. Well, it looks like I'm going from negative 1 to 1. My function, my curve, is 4 over x squared plus 2. And then we always put a dx on the end, meaning that we're going to integrate this with respect to x. We're making a bunch of rectangles underneath here, and we're figuring out the area underneath that curve. The second one I've drawn here says set up a definite integral that yields the area of the region and do not evaluate the integral. This one's a little bit different because if I look here, I'm not really going to mention things about the x-axis because it's all in terms of y. And so we could write a definite integral in terms of y as well. We can say we're going to go from 0 to 2. And notice I'm doing everything in terms of y, not x's. We're going to say we're going to go from 0 to 2 of the function. The function is y cubed. And we're going to put a dy on the end because we're talking about y's. We're finding the change in the y. The next one, what we're supposed to do is we're supposed to sketch this graph, and then we're supposed to use a geometric formula to evaluate the integral. So let's see if I can get the sketch of this picture. What I have here is 4, so that would be y equals 4. Well, y equals 4 is a horizontal line. It says to go from negative a to a. We don't really know what values those are. All I need to do is find the area underneath the curve. So I'm talking about this area, and what I have is a rectangle. So I'll be finding the area of the rectangle, which is base times height. Well, the area ends up being the base length is a plus a, so that's 2a, times the height. Well, the height of this is 4. I might have said plus, I meant times. So the area is equal to 8a. So I'm getting ready to do another problem where I'm going to use the geometric formula to evaluate the integral. So the first thing I'm going to do is go ahead and draw the picture. what I have here is this is actually y equals 6 minus x. So I'll graph that line. Has a y-intercept of 6 and has a slope of negative 1. So I'm looking for the area underneath this curve. And what I have is the area of a triangle. So I'm going to say area equals 1/2 base times height. I look at the triangle and I can see the base of it is 6. And I can also see the height of it is 6. So the area of this triangle ends up being 18. I want to look at a few more of the properties that we can do with integrals. Those are that we can take an integral that goes from a to b, and we can split it up and take it from a to c plus the c to b. So we can split it up into intervals. The second one I want to talk about real fast is that we can take this constant k. So if k is being multiplied through the function, we can actually pull the k out front and then integrate it. The last one is we can take two functions that are being added together and we can separate them into two separate integrals. So let's look at a couple problems. This one just says I'm going to go from 2 to 2, and earlier we talked about if I had something that went from A to A, the answer would be 0. So the area underneath this curve right here, since I'm going from 2 to 2, happens to be 0. This last example I have information about an x cubed dx, and I have information about an x, and then I have information about dx. So let's think about what I could do to figure out this answer right here. I'm on the wrong slide. I have information about an x cubed, which is what I want, and I have these two pieces of information I can't really use. So we're going to split this up into 2 to 4, x cubed dx, using that last property we just talked about, plus the integral from 2 to 4 of 4 dx. Now, I know what this is because it tells me it's 60. Plus, we're going to have to think a little bit about what this means. Well, this is the graph y equals 4. I'm going to find the area underneath the curve from 2 to 4. So I'm really looking for the area right here underneath this curve. That's what this implies. So what I really have is I have a base of 2 and a height of 4. So that means that my area underneath this curve is 8. So my final answer to this problem would be 68.